Yes, my screen is visible to you guys, right? Okay, so welcome you all. So today we'll be seeing about jet propulsion questions from 2015 Aerospace Gate paper. So myself Akshay. So let us jump on to the questions. So in 2015, we had around 7 questions from a core jet propulsion. There are some questions from rocket propulsions too. So, but from jet propulsion, we had 7. So out of which like 3 were 1 mark question and 4 were 2 marks question, totaling about 11 marks. So the pattern is almost same, like you can expect somewhere between 10 to 15 marks from core jet propulsion. It depends on rocket propulsion part. Sometimes they will keep some more marks on rocket propulsion side. Sometimes they will skip there and they will add more in the core jet propulsion. Okay. So the first question is which one of the following aero engines has the highest propulsive efficiency? So can anybody quickly say what should be the correct option among these? Okay, so let us look at the options carefully. So we have turbojet engine without afterburner, turbojet engine with afterburner, turbofan engine, ramjet engine. Is the question could have been much more specific, but still we can answer this question. The ramjet engine is not going to have much of a propulsive efficiency because the purpose of ramjet engine is different. So, and turbojet engine and turbofan engine, this is where the comparison comes. And turbojet engine with afterburner, again, not going to have much of an propulsive efficiency, because how do we define our propulsive efficiency is like 2 alpha divided by 1 plus alpha, where alpha is forward speed to jet exhaust velocity. So we know with afterburner we can increase the jet effective velocity, but doing so alpha will decrease. So if alpha decreases, my propulsive efficiency is also going to decrease. So this is not an option. So we have to compare with option A and option C now. So turbofan engine usually gives a more propulsive efficiency because there is a fan action. So which purely results in a propulsive thrust from the fan. So that is why turbofan engine always gives a much more propulsive efficiency compared to turbojet engine compared on a same operational range. So that is the part in the question they should have specified, but we can assume it for a given Mach number and less than sonic condition. So that's the norm we will take now. So except for ramjet, all other engines can fly in the subsonic range. Okay, so from this one we can pick option C as our correct option. Okay, the next one, the stoichiometric fuel to air ratio in an aircraft engine combustor varies with the compressor pressure ratio as follows. So they have given 4 options. 1 increases linearly, B decreases linearly, C is independent, D increases non-linearly. Yes, so option C should be correct, right? Because you see, it's a stoichiometric fuel to air ratio. It really doesn't care how compressor is delivering or how much of a pressure you are expecting at the entry of the combustion. It stoichiometric fuel to air ratio is purely based on the theoretical calculation. So I have some hydrocarbon fuel, say CXHY, some hydrocarbon fuel, which is mixing with the oxygen and nitrogen, that is the air, which has like 79% nitrogen and 21% oxygen. So which gives me a chemical balance of CO2 plus H2O plus N2. So if I balance this one, so say like I don't know exactly how much I have to balance. So first I'm just going to do a balance. So if I have Cx, then I should have XCO2. If I have Hy, then already H2 is there. So it is going to be Y by 2 H2O. So if I have X plus Y by 2 of Y by 2 of O and XO2, so this is going to give me X plus Y by 4 of O2. So that balances the equation properly. So then nitrogen is just X plus Y by 4 times 3.76 N2. So this much is the balance. So all we are doing here is like theoretical balance. So it really doesn't care how much a compressor is delivering or how much the compressor pressure ratio and all. So it's an independent parameter, right? Option C has to be correct. Okay. The next question is isentropic efficiencies of an aircraft engine operating at a typical subsonic cruise condition with the following components: intake, compressor, turbine, and nozzle are denoted by eta I, eta C, eta T, and eta N respectively. Which one of the following is correct? Okay, this question is a bit ambiguous because without the data, it is really hard to comment on which one of these is going to give me highest efficiency. But straight away, I can omit two options, that is option A and option B, because no, yeah, so I can omit these two options because I know for a reason turbine efficiency cannot be less than compressor efficiency. So using that condition, I can actually omit this one. Option D is a possible answer, but again, here the question is whether intake efficiency is higher or the turbine efficiency is higher. This is where we actually need the data to compare, because intake is just a duct. Okay, so there is only energy transformation, say subsonic intake, energy transformation. Only adiabatic loss you can actually see here is due to irreversibilities. Okay, whereas in the turbine you can see either due to energy transfer or due to energy transformation. The both part will be there. But the question here is whether they are operating in a favorable condition or adverse condition, whereas intake is operating at an adverse pressure gradient, where turbine is operating at a favorable pressure gradient. So that makes a difference. Okay, so this is where the judgment is really hard on this particular question. As far as my view is concerned, option C and option D both are like a bit difficult to say which one is correct. So, but we can choose option C as correct answer, given that turbine also has aerodynamic losses, plus irreversibilities. So based on this assumption, we can take this as an option, but still in my point of view, this question needs a much more information to pick the correct answer. Okay. So the next question is, it's a 2-mark question. Air enters an aircraft engine at a velocity of 180 meters per second with a flow rate of 94 kgs per second. The engine combustor requires 9.2 kgs per second of air to burn 1 kg per second of fuel. The velocity of gas exiting from the engine is 640 meter per second, the momentum thrust in Newton developed by this engine is? This very interesting question. It's a very straightforward question, but the only catch here we have to make is the way how they have defined fuel to air ratio. Because if I look at my thrust equation, say thrust produced by an aircraft engine, that can be written in terms of momentum thrust, mass flow rate of gas times Cj plus minus mass flow rate of air times the inlet velocity plus the pressure thrust, Pe minus Pa times Ae. So since in the question they are asking only to calculate the momentum thrust, so I can actually neglect this part, right? So now I have mass flow rate of gas minus Cj minus mass flow rate of air times Ci. So that is the thrust minus inlet momentum drag. So if I use that idea, so the mass flow rate of gas can be written as mass flow rate of air plus mass flow rate of fuel times Cj minus mass flow rate of air times Ci. This is my momentum thrust. So now if I take mass flow rate of air common, so this becomes 1 plus fuel to air ratio, that is mass flow rate of fuel to mass flow rate of air times Cj minus Ci. So now you look at the question carefully. Everything else is given. Cj is given, that is 640 meter per second. Ci is given, that is 180 meter per second. And mass flow rate of air is given, 94 kgs per second. Now only unknown is F, that is a fuel to air ratio. So that one we have to calculate, but it is given such that the statement they are given the statement such that 1 kgs per second of fuel burns with 9.2 kgs per second of air. So that means my fuel to air ratio is going to be 1 kg per second divided by 9.2 kgs per second. So this is my fuel to air ratio. So we cannot take 1 divided by 94 because it is given in a statement like I have to use this as my fuel to air ratio. So this is the only catch you have to make out here. So other than that, like the question is very straightforward. Once you get the fuel to air ratio, so let us move to the next page. So I can get mass flow rate of air times 1 plus F times Cj minus Ci. So mass flow rate of air, we know that is 94. 1 plus 1 divided by 9.2 times 640 minus 180. So if you calculate this one, you should be able to get something around 49,779.13 newtons. So let us just look back the given options. 49,779, that is option D, right? Yes. Let us move on to the next question. Following are the operational parameters of an axial compressor stage. So air mass flow rate 24 kgs per second, static temperature of air at the rotor inlet 278 Kelvin, velocity of air at the rotor inlet, that is given like zero whirl velocity 140 meter per second. Work done on the compressor rotor is 734 kilojoules. Isentropic efficiency of the compressor stage 0.86. Ratio of specific heats is 1.4. Specific heat at constant pressure, that is 1005 joules per kg Kelvin. The stagnation pressure ratio across the axial compressor stage is. Okay, this is fairly a straightforward question, but the important point you have to observe here is there are some hidden information. The first hidden information, the unit of work done, right? It is not per mass flow rate. It is given in the units of power. So like, sorry, is given in the units of energy, kilojoules. So it's not per kg. So this is one hidden information. The next hidden information is zero whirl velocity. What do they mean by zero whirl velocity? That means it's entering with absolute velocity vector equal to axial velocity vector. So there is no direction change with respect to axial velocity vector to the absolute velocity vector components. So let us try to get this information straight. So let us draw a small control volume for the compressor stage. Okay, so I have inlet conditions, that is mass flow rate of air is given 24 kg per second. Then they are also given zero swirl velocity or whirl velocity. That means my absolute velocity, which is also equal to axial velocity, equal to 140 meter per second. That means CT1 is equal to 0. That's the hidden information. And the efficiency of the compressor is given to you 0.86. And the properties of the fluid is given gamma 1.4 and Cp 1005 joules per kg Kelvin. And work done by the compressor stage is given, that is 734 kilojoule. Right. So these are the informations we have. So what they are actually asking you to calculate the pressure ratio, right? So I have efficiency of the compressor that is given by actual work to ideal work. Sorry, ideal work to actual work. So that is going to be T02 dash minus T01 divided by T02 minus T01. So if I take T01 common, so that gives me T02 dash divided by T01 minus 1 whole divided by T02 minus T01. So this can be written as, so see if I have a TS diagram, let me just use the different color. If I have a TS diagram, so P01 to P02, I am raising the pressure in the axial compressor stage from state 1, that is at T01 at entropy S1. So this is T and S curves. So if I have this constant entropy line, okay, this is S1 is equal to constant line. So now my actual temperature at the exit is going to be T02. So corresponding to actual pressure. So that is given by my actual curve. So now I have this delta S increase due to irreversibilities. So what if the same pressure is raised in an ideal way? Then you would have expected this pressure curve to meet this constant entropy line somewhere over here. That would have been your ideal work required to get the same pressure rise. So that means T02 dash and T01 falls on the constant entropy line. So I can use isentropic relation only to this ratio, right? So if I use that one, I can write T01 times. So the pressure ratio P02 by P01 that I will represent as pi c, pressure ratio in the compressor, to the power of gamma minus 1 by gamma minus 1 divided by, this is T02 minus T01, that is delta T0 in a compressor stage, right? So this is the actual temperature change in the compressor stage. This is the actual pressure rise in the compressor stage. So now we have the formula for efficiency in terms of all the actual variables, right? So now I can replace for this pressure ratio because we are asked to calculate pressure ratio, if I am correct. Yes, we are asked to calculate the pressure ratio. So now if I want to write for the pressure ratio, that is going to be eta c times delta T naught in a stage divided by T01 plus 1 whole to the power of gamma divided by gamma minus 1 equal to the pressure ratio. So I am keeping pressure ratio right hand side and shifting all other variables to other side. So now eta c is now T01 is also none because T1 is given to us. T1 is given to us in the problem, that is 278 Kelvin. C1 is given, so I can calculate T01. Eta C is now. So I have to calculate delta T0 stage. So that I am going to calculate from the work done information. So let us try to calculate the unknowns. So T01 is equal to T1 plus C1 square divided by 2Cp. So here I am using the energy equation, the help of the energy equation for adiabatic study inviscid with no body forces. Okay, this is the form of energy equation. Okay, so C1 square divided by 2Cp. So here we always use the absolute velocity component to calculate the T01. We should not forget. Okay, so if I calculate that one, 278 T1 and C1 is 140. So I should able to get T01 to be something around 287.75 Kelvin. That is my T01. So one unknown is solved. So the other unknown is delta T0 stage. So we know from basics of thermodynamics, if I equate work done, so that is going to be work done by the compressor, that is going to be mass flow rate of A times delta T0 stage multiplied with Cp. So this is actually the total enthalpy change. H02 minus H01 is equal to work done. So this is given by first law of thermodynamics, right? The internal energy change is given by the work done on the fluid, right? So now write it for delta T0 stage. So that is equal to work done by the compressor divided by mass flow rate of the air times Cp. So everything is known to us, 774 kilojoule, and mass flow rate is 24 kgs per second. Cp is 1005 joules per kg Kelvin. So you can get delta T naught stage to be 30.4312 Kelvin. So now everything is known. So just keep this equation back into the pressure ratio equation we arrived. So that is phi c is equal to 1 plus compressor efficiency times delta T naught stage divided by T naught 1 whole to the power of gamma by gamma minus 1. So if we keep back that one, so you should be able to get the pressure ratio in the compressor stage to be something around 1.3562. So I usually practice with 4-digit accuracy, but it's up to you. You can go with 3 digits also, but don't keep 2 digits. So at least try to keep it 3 digits. Okay. So you can write once you want to keep it in an answer, you can go to second digit accuracy, or you can go on to put the third digit. It's fine. Okay. Sometimes in the question they will ask how many digits you have to keep and whether you have to accurate or round off, or you just have to approximate. So that information they will give in the question itself. Okay. So now we will move to the next question. That is, a centrifugal air compressor is operating at the following conditions. Inlet stagnation temperature, sorry, inlet stagnation temperature is 288 Kelvin. Inlet stagnation pressure is 1.15 bar. Exit stagnation temperature is 454 Kelvin. Exit stagnation pressure is 4.8 bar. The energy loss due to non-isentropic compression per unit mass flow of flowing air, that is ratio of specific heats for the fluid, is gamma is 1.4, and the specific heat at constant pressure is Cp 1005 joules per kg Kelvin. So the loss due to non-isentropic compression per unit mass of flowing air in kilojoules per kg, that's what we have to calculate. Okay, so for this question, it is easier if you draw the TS diagram, right? So let us try to draw the TS diagram for this question. First, let us